Hello listeners, I am Dr. Anuj Sharma working in Center for Advanced Studies, which is in campus research driven institute of Dr. APJ Abdul Kalam Technical University located in Lucknow. So, we are discussing the subject fundamentals of mechanical engineering and mechatronics. It is for first year students, and today we are going to have discussion on the shear force and bending moment diagram. So, actually this is a long topic and cannot be covered in a single lecture. So, we divided it into two parts. So, today in this lecture it is for part 1, and in the part 2 we will also continue some topics related to the BMD and SFD. So, these are the outlines of my today's lecture. We will discuss and quickly we will go through the different types of beams and loading conditions, though we have discussed this in the past and lectures also, but we will have a very quick review. So, that you can start with this lecture itself. Then we will discuss what is shear force, what is bending moment, then what is shear force diagram and bending moment diagram, and the important part of this is relation between the intensity of loading, shearing force and bending moment. So, what relations it has? If time will permit, then we will have a small problem also. So, what are the beams? So, beams are basically the horizontal structural member. So, this is very important term. These are the horizontal structural member and they supports the load acting over it in its vertical plane. So, load may be inclined or vertical, but that always be in the vertical plane of that particular beam. So, different types of beams we have already discussed, but let us again quickly will discuss this. So, if we will classify the beams, it can be categorized into two categories. First is the statically determinate beams. So, these are three types of beams. So, simply supported beams means it will be supported by two supports and just we will have two reactions R1 here, R2 here and different types of loading. Loading may be of three types. It may have the point load, it may have the UDL and it may have the varying distributed load. So, these three types of loading it can have. So, depending upon the application and types of loading we can have different types of beams. Cantilever beam means its one end is fixed and one end is free. So, there may be also different types of loading here and we will have three reactions at this fixed support, one reaction and two reaction. These two reactions would be mutually perpendicular to each other and third reaction will be the movement. So, this kind of beams will have three reactions. Now, the overhanging beams means, so this is the beam if it is overhanged at two supports may be on the one side or on the both side or on the right side, and here the loading, different types of loading we have already discussed in the previous lectures. So, depending upon this we can have these two reaction, but not more than two supports. So, these are the beams which are statically determinate. Why statically determinate means we have three equations, sigma f x equals to 0, sigma f y equals to 0 and sigma m equals to 0. So, these three are the equations of equilibrium. If any beam which can be solved using these three equations of equilibrium, it is the statically determinate beam, and if these three equations are not sufficient to solve any beam or beam reactions, then that beam will be known as the statically indeterminate beams. So, these beams are not in your syllabus, so you not need to study in this particular subject, but later on when you will go to the second year you will study these mechanics of solids. So, then you will have to study the different types of beams in deeper domain. So, continuous beam means if we have more than two supports like this. So, this is the continuous beam. Fixed beam means if both the ends of the beam are fixed. So, this is the beam, this is not in this particular syllabus, and propped cantilever means let us say one end is fixed and other end is propped by some support. So, these kind of beams are not in the syllabus, but we should know to differentiate these beams. So, we will focus on our study on the statically determinate beams. Now, types of loading already we have discussed. Concentrated load means let us say this is the concentrated load, this is the uniformly distributed load. So, the information which we require here, let us say it is W Newton per meter and it is the length L. This is the point A, this is the point B. So, while calculating the bending moment, we need to convert this into the point load. So, how it can be converted, that we have already discussed in the previous lecture. So, this is the A, this is the B. So, we have to convert this, the total value of this load will be W into L, W multiplied by L, and where it would be applied? It would be applied at the midpoint. So, it is L by 2, it is L by 2. So, if you want to convert UDL into the point load, because if we want to calculate the moment about this point A, so we can easily calculate. So, sigma m A, if we want to calculate here, so that would be equal to W L, this is the load, multiplied by this distance is what? L by 2. So, the moment of this load at this point will be W L square by 2. From here it would be very difficult to calculate the movement. So, that is why we need to convert it into the point load. Similarly, for the varying distributed load, let us say this is the triangle and this is L, total length is L and the intensity is W. So, also we have to convert it into the point load. So, this is the A, this is B. So, how it can be converted? So, this is the beam, the load, the value of this load intensity would be equal to the area of this triangle, and what is that area? That area is half into what is the base? Base is L, height is W. So, that would be equal to W L by 2. So, this is the total load, and where it would be applied? So, we know the center of gravity of this particular triangle would be at 1/3 from this distance from B. So, this distance would be L by 3 and this is the point A and this distance would be L 2L by 3 and the load value would be W L by 2. So, if you want to calculate the movement about point A, so movement about point A, that would be equal to W L by 2 multiplied by 2 L by 3. So, 2 will be cancelled out. So, W L square by 3. So, likewise we can calculate the movement of these two types of load, because for calculating movement of this point, let us say this is W, this is L from here. So, here you can easily calculate the movement for point loads. So, anyhow we have to convert all the forces, different types of forces into the point load, then only we can calculate the movement about any force, about any point. So, now let us discuss what is shear force and what is bending moment. After this we will discuss the bending moment and then we will have to plot the shear force and bending moment along the length. So, those diagrams are known as the shear force and bending moment diagram. So, here if you will see, the shear force by definition is, let us say we want to calculate the shear force at any point. So, shear force at any point along a loaded beam means, let us say different types of loads are given. So, for example, let us consider this beam. So, this is a point A, this is point B, this is normal reaction R1, this is normal reaction R2. So, these are the two supports, here you can see. Now, let us say one load W1, one load W2, these loads are acting at this point. So, if we want to calculate the shear force at this point, let us say this is the point, this is the section where we want to calculate the shear force. So, what is shear force? So, it is at any point if you want to calculate, it is a it is the algebraic sum of all the vertical forces. This is very important, algebraic sum of all the forces acting on one side of that point. Let us say we want to calculate the movement about shear force about this point. So, either see the left side or see the right side, right. So, either see left side or right side. So, that will give you the same result, either left or right. So, let us say for simplicity and till the end of this lecture or end of this topic, we will fix our sightness on the left side. So, we will see always the left side of that section. So, algebraic sum means you add all the forces by considering their sign convention. So, for sign convention we consider that the upward force as positive and downward force as negative. So, always we will have this standard notation, right. So, if you will see on the left side of this beam, so we are having three forces. So, shear force at this point. So, let us say shear force at section, this is section 1 So, section 1 shear force 1 is equal to, that would be equal to R1 is upward, so it is the positive, minus W1 it is downward, that is why negative, minus W2 it is negative. So, likewise we can here see that this is the shear force. So, what this shear force will do? So, this shear force will definitely will help in finding out the shearing of this beam. So, how we can calculate the shearing? Shearing means when we apply this force and due to the material failure it may happen here. So, this portion of the beam and this portion of the beam, if we separate the beam from this section. So, the net force, so overall force which is acting here, that is the shear force. So, that shear force at this point will be acting this much, whatever we have calculated, and the same shear force on the right side will try to move this point this beam downward. So, if you see here, so this is the force at this point. So, what we have calculated. So, this shear force is what? This is the shear force. So, shear force will try to resist the shearing of the beam. So, if the beam strength will not be sufficient to resist this shear force, so the breakage or the slippage or the shearing of the plane along this section will takes place, right. So, we have to avoid this while designing. So, this is the shear force. So, for mathematically if you want to calculate shear force, so it is very simple, just remember one thing, to see any section and see either on the left side or on the right side. So, we have fixed that we will always see on the left side. So, always try to add the forces on the left side algebraically, then we will get the value of shear force. Now, similar situation is for the bending moment. So, we should know what is bending moment. So, bending moment is what? Bending moment means force into displacement. So, likewise we have to see. So, it is also in the similar fashion, bending moment if we want to calculate at any point, that is equal to the algebraic sum of the moments of all the vertical forces acting on one side of that point and about that point. So, here also we will see, let us say this is the beam, this is the reaction R1 R2 and we have one force here and we want to calculate, let us say this distance is 1 meter, this is 10 Newton and whatever this is R1 R2 we can calculate. So, this is 1 meter, this is 4 meter, let us say like this. So, if you want to calculate the moment about this point, which is at a distance of from here, it is also 1 meter and it is 4 meter. So, total beam length is 6 meter. Now, let us say this is the point C where we want to calculate the moment. So, moment would be how much? If we want to calculate the bending moment. So, bending moment at C point will be equal to the algebraic sum of all the. So, on the left side you can see the R1, if we fix this point. So, the moment of this force is R1 into 2 and the moment of this point, this force is 10 and which what is the distance total? This distance is 1 meter. So, minus 10 into 1. Now, why I have taken this as positive and this as negative? So, we have to take again the sign convention. So, for sign convention we consider these two terms, sagging and hogging. So, if we have a beam like this and if we get the moment like this and after bending if it go like this, so it means it is the sagging bending, and if it bends like this, so it is the hogging. So, we always consider this bending as positive, this bending as negative. So, we can easily see here also, you can see. So, this is the beam, let us say this is the beam and we if we provide the moment like this. So, it always try to give the bending in the smiling face. So, smiling face, just to remember the just for the ease of remembering, we can say if we have the smile face, then the bending will be positive. If we have the sagging face, sad face, then it is the negative bending moment. So, if you see the point, let us say if we see, because we are always seeing the left side. So, left side means here, if left side means this. So, it means left side bending moment. So, we have to take the sign convention, if left side, if on the left side clockwise is positive, anti-clockwise is negative. So, we are seeing only this. So, you can see positive bending moment mein if we have the clockwise movement on the left side, that would be considered as positive, and if we see the right side, anti-clockwise will be positive. So, it is the point to remember. In case of negative bending moment, if we see the left side, if bending moment is counterclockwise. So, this is the counterclockwise. So, it means the counterclockwise is negative, we have written here. So, we are looking only the left side. So, here you can see if we write the moment about this point. So, what you see, it is the r 1 into t, it is the positive bending moment. We are seeing the left side and we are getting positive bending moment. So, that is why it has positive. Now, about this point, this force is going like this. So, this is counterclockwise. So, that is why we have taken it as negative. So, you can add. So, this is the process by which we can easily calculate the bending moment about any point. Now, what is the shear force and bending moment diagram? So, for example, if we consider this as a beam. So, if this is the beam, these are the reaction and we have calculated the reaction. I will discuss some numerical problems also. So, this distance is L by 2. So, it means this load is acting at the midpoint. So, you can see, so we have different points while moving from A to B through C. So, we have to move from this point to this point for length L. So, we have infinite number of points. So, it means we can calculate the shear force or bending moment corresponding to any point, or the simplest way is if we can draw a pattern by which looking at the beam or bending moment or shear force diagram, we can easily calculate the bending moment or shear force at any particular point. So, this is the graphical representation. So, shear force and bending moment diagrams are the graphical representation of the variation in the shear force and bending moment along the length of the beam. So, if we take on the x axis the length of the beam, so this is the length of the beam, and on the y axis if we take the variation of shear force. So, if we plot it on the xy coordinate system, then the diagram which we will get, that is the shear force diagram. In short, we call it as shear force diagram ko SFD, right. Similarly, if we take the x axis, on along the x axis we take the length, and along the y axis if we take the bending moment variation. So, that is the bending moment diagram. So, it is known as the BMD. So, you can see, so why I have plotted the diagrams SFD and BMD just below the beam, because if we it is easier to locate different points here and we can easily correlate the SFD and BMD with the beam. Ki let us say if you want to know the bending moment diagram at this particular point. So, you can come down and you can see. So, this is the bending moment diagram, this is the shear force. So, what is the shear force? That would be the W by 2. How it has come, I will discuss in detail in the numerical problem. So, it means at this point it is W by 2, right. Let us say, but it is negative here. So, why it has negative, we will discuss later on. And if we want to calculate the bending shear force at this particular point, so you can come down and you can see this is the positive W by 2. You can see here W by 2 and it is a positive value. Similarly, for bending moment, you can say the variation is like this. So, it is a linear variation and it is decreasing from there, and the value is W L by 4. So, this is the maximum value here. So, likewise we can easily see the variation in the bending moment, or interestingly you can find. So, the bending moment is maximum where the shear force is 0. So, you can see the shear force is 0 at this point. So, it means here we are getting the bending moment maximum. So, these are some points upon which we can have different interpretations ki where the bending moment is maximum, where it is 0, and what should be our designing of the beam. So, while designing the beam we always consider the BMD and SF diagrams. Similarly, for this we will discuss this also. So, you can see the variation here. So, this is the SFD and this is the BMD, right. So, this is a variation from here to here WL to 0 from this end to this end. So, likewise we will discuss this in detail. Now, the interesting is and very important this is the what is the relation between the intensity of loading, shear force and bending moment. So, let us say this is the beam. So, we have considered this is the beam and we have assumed that this is loaded with some intensity. I do not know what kind of intensity, but it is in this particular case it is looking like the uniformly distributed load, but it is not actually uniformly distributed load, it may be like this whatever it is. So, just anonymously we have taken any intensity. So, let the intensity is W per unit length. So, W Newton per unit length. So, out of this beam what we have considered? We have considered this particular segment. So, this is this segment. So, we have considered the total length is let us say L. So, out of this at a distance of x from one end we have considered this element elementary element whose length is dx, right. So, we have cut this particular section. So, we want to interpret this, then we can integrate it or we can do the different processes to get the effect on whole beam. So, let the bending moment at x be m. So, we know the bending moment and shear force diagram varies from one end to another end. So, what we see? So, let us say at this end the bending moment is m and at the another end after a distance of dx let the bending moment is decreasing or increasing. We have taken here m minus delta m, you can take m plus delta m also. So, that is not a problem. So, on this left side let us say it is m. So, we have considered a minor variation. So, delta m is a variation. So, on the other side it is m minus delta m. Similarly, we have taken this force, shear force is F on this end and after a distance of delta x let the shear force is F minus dF, something is decreased. So, in the first slice we have seen that force if we cut the beam into two portion and it is shearing off. So, what happens on the left side if it is moving upward. So, then on the right side the same intensity of force will go down, but here we have considered the elementary length dx delta x. So, we have considered that there is a small variation from left to right. So, let us say the shear force is F on the left side and on the right side of that particular cut section it is F minus delta F. The load on the elementary length delta x be taken as uniform whose intensity may be taken as W per unit length. So, this is I have already told you that I have taken this intensity for our simplicity. It can be non-uniform, but for our simplicity we have taken it uniform W unit per length. And let us consider the equilibrium of the beam element A, B, C, D. So, for this we consider the equilibrium of this portion. So, for equilibrium if we will apply the equations. So, in the vertical direction if we will apply, so sigma f y equals to 0. So, it means on the upward side the force is F upward minus F minus delta F is the downward minus W into dx. So, per unit length it is W. So, for delta x what would be? So, W into delta x. So, this is the equation. Now, if we will simplify it, we will open the bracket and we will simplify. So, this F will be cancelled out by this when you will open the bracket. So, we will get the delta F minus W into delta x and it means we can have delta F upon del x is equal to W. This we have got. So, if we put the limit tends to 0, so delta F can be become dF upon dx. So, dF upon dx is W. So, this is the first relation. So, what is this relation? So, first, so differentiation of shear force is equal to the load intensity. So, the relation between the load intensity and the shear force is what? So, if we differentiate the shear force, we will get the load intensity. So, this is the first relation. Now, taking moment of all the forces about point A, right. So, if we see the point A, what is the total moment? So, for this the moment is on the left side it is m, on the right side it is minus, means it is clockwise na, m minus delta m, it is anti-clockwise, and rest of the moment would be, let us say this is the beam and this is the moment. So, this distance is delta x by 2. So, let us say this point is A. So, this intensity of this is what? W into x. So, if we replace this UDL by the point load, as already we have discussed. So, the point load would be Wx and it will act at a distance of delta x by 2. So, the moment of this is Wx into delta x by 2. So, you can see the moment is F minus delta x into dx, that is the on the right side it is anti-clockwise. So, that is why we have taken as positive, right. So, this is the force, sorry, this is the force, right. So, F minus delta F, now we have 4 movements. So, first movement is about this point F minus delta F into this distance. So, this is the positive clockwise. Now, M minus delta M, it is the anti-clockwise. So, that is why we have taken a negative. Next is W into dx by 2. So, Wx into dx by 2, this is the clockwise. So, W into dx by 2, it is the clockwise, plus M, M is also clockwise. So, there are 4 movements. Now, you can open. So, it is F into del x minus del F into del x minus M plus delta M plus W into del x square by 2 plus M. So, just what we did, we have just opened the bracket. So, now what we can do, we can again simplify it. So, this reaction we have got, this equation we got. Now, what we can see, delta x is very small. So, the square of the very small quantity is again very small. So, we can neglect the smaller quantities. So, if we will neglect the smaller quantities, then what we will get? We will get the F into delta x plus delta M, that is equal to 0. So, this is delta M, sorry. So, this is again very small. So, you can neglect this, you can neglect this. So, what we will get? F into delta x plus delta M equals to 0. So, now what you will get, delta M upon del x is equal to minus F. You can put the limit tends to 0. So, we will get this expression. So, this is what. So, when you differentiate the movement, bending movement with respect to x, so what you will get? You will get the minus of shear force. Negative sign indicates that there is a relation between the bending moment and the force is negative. So, similarly, we have taken the limit. So, we have put del dm by dx is equal to minus f. So, you can see ki if we want to determine the maximum value of the bending moment. So, what we can do? We can differentiate this quantity. So, upon differentiation what we will get? We will get d square m upon dx square is equal to 0. It is the constant. So, if we will differentiate it, so it will become 0. So, it means what we can see from here. So, for delta m dm by dx to be maximum, so if we will put here, so we will get the force should be, shear force should be 0. So, the rate of change of bending moment with respect to x is equal to the shear force. Whenever bending moment is maximum or minimum, the shear force is 0. So, when we will get the maximum bending moment? So, it is the point where the bending the shear force would be 0. So, we can see from this. So, this is the relation basically. So, if we differentiate the shear force, we will get the load intensity. If we will double differentiate the bending moment, we will get the load intensity. If we will differentiate the bending moment, first derivative of the bending moment, we will get the shear force. So, likewise, we are moving from high to low degree of differentiation. So, this is the relation between the intensity of loading, shear force and bending moment diagrams. So, bending moment. So, I hope you have understood the basic concept of the shear force and bending moment diagram, the difference between these two, and in the next lecture, lecture 8, we will take some numerical problems to understand how we can draw and determine the bending moment at different points, shear force at different points, and how we can draw the SFD and BMD of different beams under the different loading conditions. So, thank you for watching. Thank you so much.